At the outer edge of our solar system lies Pluto, a celestial mystery that has fascinated astronomers and space enthusiasts alike. Once the ninth planet in our solar system, Pluto's reclassification as a dwarf planet did not diminish its appearance. However, new information has emerged in the astronomical community. There are whispers of a possible conflict between Pluto and its neighbor, Neptune. What does this mean for the future of our solar system? Are we about to witness an unprecedented world crash? The story of Pluto is one of mystery and speculation. Since its discovery in 1930, Pluto has fascinated scientists with its unusual orbit, one that is different from the main planets in our solar system. Unlike the circular orbits of its fellow planets, Pluto's journey around the Sun is very slow, taking 248 years to travel outside the solar system. Adding to the mystery is the tilt of Pluto's orbit, which has an angle of 17.1 degrees relative to the plane of the orbit. But what really sets Pluto apart is its conjunction with Neptune's orbit, a conjunction that occurs about 20 years in each orbit. The tug-of-war between Pluto and Neptune has long fascinated astronomers. Despite the dangerous proximity, there was no crash. But why? The answer lies in the complex dance of gravitational forces that govern their orbits. The nature of the orbital space ensures that Pluto crosses the path of Neptune, which is more than 90 degrees from Neptune. This shield prevents the two celestial bodies from getting too close. But can this simple balance be a distraction? Could it be that one day we will see a terrible collision between Pluto and Neptune? To understand the dynamics involved, we need to examine the dynamics of the three-body problem, a challenge that has puzzled scientists for centuries. The three-body problem involves predicting the motion of three celestial bodies such as Pluto, Neptune, and the Sun based on their interactions. In the case of Pluto and Neptune, this problem is exacerbated by the presence of other large planets in the solar system, such as Jupiter and Saturn, which have a strong planetary influence. Astronomers have identified several key factors that contribute to the stability of Pluto's orbit. As mentioned earlier, the lengthening of the orbit is an important step in keeping Pluto and Neptune at a safe distance from each other. In addition, the spring and fall of Pluto's orbit will be significantly above Neptune's orbital plane when the two bodies are closest to each other. This extra layer of protection reduces the risk of collisions. But despite these stabilizing forces, Pluto's orbit is unstable. Numerical simulations performed in the late 1980s show that even small variations in Pluto's position or speed can lead to large changes in its orbit in 1,000 years. This chaotic behavior is a reminder of the delicate balance that exists in our solar system, one that can be disturbed under the right conditions. The gravitational influence of the giant planets in the solar system cannot be overestimated. Jupiter, with its massive mass, exerts a powerful influence on all the planets in the universe, including Pluto. Saturn, although smaller in size, plays an important role in shaping the lives of nearby celestial bodies. These two giants work together to stabilize Pluto's orbit, ensuring that it remains on a very stable path for billions of years. However, Neptune has a unique relationship with Pluto. The two bodies are in a 3:2 resonance, meaning that for every 3 revolutions of Neptune around the Sun, Pluto completes the orbits. This noise helps maintain Pluto's orbit and prevent it from crashing into Neptune. But what if this delicate balance is disturbed? Could the impact of another object, such as a passing asteroid or comet, change Pluto's orbit and put it on a collision course with Neptune? Despite the stability, Pluto's orbit remains a source of intrigue and concern for astronomers. The concept of periodic chaos, where small changes in the position or speed of a celestial body lead to large changes in its orbit over time, is especially true for Pluto. Even a small change in Pluto's position or speed can have a big effect on its long path. Virtual simulations have provided valuable insight into the chaotic nature of Pluto's orbit. By making small adjustments to the starting conditions of these simulations, astronomers have seen how small changes can produce wildly different results. This surprise highlights the challenges of predicting Pluto's future trajectory and raises questions about the long-term stability of its orbit. The collision between Pluto and Neptune has been of great concern to the astronomical community. Prominent astrophysicists such as Neil deGrasse Tyson and Michio Kaku expressed concern about the results of that event. Tyson, who played an important role in reclassifying Pluto as a dwarf planet, has warned that the three-body problem is very dangerous, saying that the collision between Pluto and Neptune will be long. But what were the results of that meeting? For Pluto, this match is bad. Because of its small size and icy structure, Pluto was destroyed by the force of the collision, scattering debris throughout the solar system. This debris could threaten other planets and moons, and could threaten the stability of the entire solar system. Neptune, though larger, did not die. This collision could change Neptune's atmosphere and have significant consequences for the dynamics of the planet's atmosphere. Disrupting the balance of the solar system raises troubling questions about the long-term stability of our planetary system. Leading theoretical physicist Michio Kaku has a unique perspective on the potential collision between Pluto and Neptune. Kaku's work in string theory and his understanding of the relationship between celestial mechanics and theoretical physics provide a deeper understanding of the forces at play. Kaku sees the study of Pluto's orbit as a window into the future. By understanding the planetary interactions and orbital dynamics of celestial bodies like Pluto, we can gain valuable knowledge to help guide the universe and beyond. This knowledge can help us predict possible disasters and plan missions to the outer regions of the solar system. Kaku also emphasizes the connection between celestial mechanics and basic physics principles. The gravitational interactions between Pluto, Neptune, and other planets are not random, but they affect the fundamental laws of the universe. By studying these interactions, we can gain a deeper understanding of the fundamental forces of the universe and how they shape the universe. Pluto's orbit is also related to its location in the Kuiper Belt, a region of the solar system beyond Neptune that is inhabited by many small, icy bodies. As one of the largest members of the Kuiper Belt, Pluto's orbit takes it deep into this region, where it interacts with other Kuiper Belt objects. The energy of these objects, along with the overall mass distribution in the Kuiper Belt, creates subtle disturbances in Pluto's orbit. These disturbances can cause the orbit to drift and tilt, adding complexity to the complex dynamics of Pluto's orbit around the Sun. Understanding these interactions is critical to obtaining a complete picture of Pluto's orbital mechanics. In addition to interacting with the Kuiper Belt, Pluto is influenced by its larger moon, Charon. The Pluto-Charon system is unique in that the center of mass, of both bodies lies outside Pluto. This mutual orbit creates a magnetic interaction between Pluto and Charon, affecting Pluto's orbit and interactions with other planets. Pluto also has 5 small moons: Styx, Nix, Cerberus, Hydra, and a recently discovered 5th moon. Although these moons exert little influence on Pluto, their presence adds layers of complexity to the dynamics of the Pluto system. Studying these moons provides a better understanding of how smaller bodies in the sky interact with their larger counterparts. One of the main tools for understanding Pluto's orbit is an astronomical observatory. Using ground-based and space-based telescopes, scientists can track Pluto's position with great precision. For example, Hubble's Space Telescope observations have provided valuable data on Pluto's orbit and its interactions with other bodies in the solar system. This observational data is needed to refine models of Pluto's orbital behavior and predict its future locations. The continued study of Pluto's orbit through astronomical observation is helping scientists better understand the complex atmospheric interactions in the solar system. In addition to observational data, numerical simulations play an important role in the study of Pluto's orbit. Astronomers use these simulations to explore the different conditions and consequences of Pluto's interactions with other celestial bodies. By combining many factors, including the effects of all known planets and large moons, as well as interference from other Kuiper Belt objects, scientists can predict changes future in the orbit of Pluto.